All right, let's jump right in. We usually like to think of science as this impenetrable vault of absolute truth, right? Well, in today's explainer, we're going to take a hard look at the seemingly perfect framework of the scientific method. And honestly, we're going to discover why it's actually a much messier, far more fascinating work in progress than our textbooks ever let on. We're unpacking some incredible source material today that fundamentally challenges how we view the exactness of science itself.
To start us off, let's look at the baseline definition. At its core, the scientific method is universally defined as a straightforward comparison between what you expect to happen and what actually transpires in reality. Sounds beautifully elegant, doesn't it? You formulate a hypothesis based on established laws of the universe, you run some tests, and you observe whether reality holds up its end of the bargain.
Picture it like two pristine pillars holding up the entire scientific enterprise. Over on the left side, we've got our theoretical predictions. Think of that like calculating exactly when a solar eclipse should happen using classical physics. Then, on the right side, we have our physical measurements, which is actually pointing a telescope at the sky to record the real-world data. The whole engine of discovery completely relies on this balance. We simply compare the hard data on the right to the mathematical predictions on the left, and boom, we have science.
But here's the wild part. There's a fascinating illusion hiding right in plain sight here. This universally accepted system completely ignores two massive variables, and it quietly pulls the rug right out from under our most basic assumptions. Our source material points out that we actually have an enormous blind spot on the prediction side and another equally massive blind spot on the measurement side.
Let's break this down. Section 1. The problem with predictions, or flaws in the math.
When we predict an outcome for any given scenario, we naturally lean heavily on our established mathematical and physics models. We treat these concepts as unquestionable, universal laws. We just assume, almost automatically, that these foundational tools are absolutely perfect baselines, giving us a flawless expectation of what should happen in a controlled environment.
However, the source material drops a bit of a bombshell here. It explicitly points out that the fundamentals of both are still a bit off. Yeah, you heard that right. The so-called exact sciences are actually built on slightly skewed foundations. I mean, just look at how quantum mechanics and classical gravity still completely refuse to perfectly align with one another in modern physics. There are inherent lingering flaws in both our math and our physics that we just completely overlook when formulating those pristine theoretical predictions.
Think about what that actually means. If the bedrock of your prediction is inherently flawed, what happens to your experiment? It means your entire expectation of reality is already slightly out of tune before you even step foot in the lab. We are literally building our most rigorous experiments on a framework that carries inherent inaccuracies.
Which brings us nicely to Section 2, the measurement apparatus mystery, asking the question, where does the tool end?
Okay, let's just say for a second we forgive the math. In the classical method, we still have to figure out how we actually measure the physical results in the real world. And the crazy thing is, we have no real grip on the physical boundary separating the measuring instrument from the environment itself. Think about plunging a cold thermometer into a hot liquid. The tool itself instantly alters the temperature of the very environment it's trying to measure. They literally bleed into each other.
And this brings us to a genuinely profound dilemma. At what physical point does the tool stop and the rest of the universe begin? Like, what exactly defines a measurement apparatus and what is merely the environment? When you place a physical instrument into a space to gather data, it dynamically interacts with that space. The boundary between the tool and the reality it's measuring is entirely undefined.
So we are dealing with an incredibly messy reality here. Because the instrument is quite literally entangled with the world it's observing, capturing a truly objective, perfectly isolated measurement isn't just complicated, it might actually be fundamentally impossible. The physical limits of human observation mean our tools are always, in some way, contaminating the very data they're trying to collect.
Moving right along to Section 3, grasping the true method by acknowledging our blind spots.
The source outlines a really clear path forward for how we should be thinking about all of this. Rather than just ignoring these massive issues, we have to follow these steps. Step 1, explicitly recognize our mathematical and physical prediction flaws. Step 2, actively acknowledge this measurement mystery we just talked about, because it's only by actively confronting these twin problems that we can finally get to Step 3 and truly grasp what the scientific method is actually doing.
Because honestly, blindly trusting the method prevents us from seeing the big picture. Science isn't some flawless, magical, truth-generating machine.
It's a profound, constantly evolving pursuit of understanding. And for us as learners, acknowledging its inherent structural limitations actually makes the discoveries we do achieve all the more impressive. We absolutely have to account for these flaws to truly appreciate the genius of scientific progress.
So I'm going to leave you with this final thought to chew on. If both the math predicting the outcome and the measuring tape recording it are fundamentally blurred, what are the true limits of our certainty? How certain can we ever really be about the exactness of the data we observe? It's a massive paradigm shift for how we view the information that builds our world. Thanks so much for joining me for this explainer, and I'll let you sit with that question until next time.